In this video, I'll explain what's an infinite series, behavior of an infinite series. If an is a sequence of real numbers, then the sum of the terms of this sequence, which are infinite in number, is called as an infinite series. Say, for example, this is a sequence of real numbers. Put n equal to 1, a1 you will get, second term, third term of the sequence. When you take sum of all the terms of a sequence, then you will get series associated with that sequence. See here, a1 plus a2 plus so on up to an plus so on. It's an infinite series and it is denoted by sigma notation n equal to 1 to infinity or just sigma an. Now let's see what is partial sums. If sigma n equal to 1 to infinity is the given series, infinite series, then s1 equal to the first term, s2 equal to sum of first two terms a1 plus a2, s3 equal to sum of first three terms. If you continue in this way, sn equal to a1 plus a2 plus on up to an. These are called as partial sums. This is the first partial sum, S2 is the second partial sum, and Sn is the nth partial sum. The sequence Sn is called the sequence of partial sums. Partial means you have to split the given infinite series into smaller terms, then you have to find out their sums. Now, behavior of an infinite series. The behavior of an infinite series is usually found using its sequence of partial sums. See here, sigma an, summation of an is convergent if limit of Sn as n tends to infinity equal to L, which is unique and finite. If the sequence of partial sums is convergent, then the series is convergent. So to check whether the sequence of partial sums converges or not, you have to find out the limit of Sn as n tends to infinity. If the value is unique and finite, then the sequence of partial sums is convergent, hence the series is convergent. The series is divergent if the sequence of partial sums diverges. That is, limit of Sn as n tends to infinity is plus infinity or minus infinity. Now the given series oscillates finitely if limit of Sn as n tends to infinity is finite but not unique. That means the sequence of partial sums oscillates finitely. The series oscillates infinitely if the sequence of partial sums oscillates infinitely. That is, limit of Sn as n tends to infinity oscillates between plus infinity and minus infinity. Let us take few examples to understand this. See here, first example, check the convergence of the following series. This is the given series. First, let us find out an, that is the nth term of this series. First term is this, second term is this. So, nth term is 1 by n into n plus 1. Now, using the concept of partial fractions, I can split this term as 1 by n minus 1 by n plus 1. After taking LCM, you are going to get the same thing back. So an is written in this way, that is because it will help you to simplify the nth partial sum. So to check is it convergent, divergent or oscillatory, we need Sn first. So write Sn a1 plus a2 plus on up to an, which is equal to, write the nth terms in this way. A1 is 1 minus 1 by 2 plus a2 is 1 by 2 minus 1 by 3 plus on up to an is 1 by n minus 1 by n plus 1. So this is Sn. Let me simplify this Sn first. See, minus half plus half cancels. Minus 1 by 3, next term would be plus 1 by 3, which cancels. Here 1 by n, the previous term will be minus 1 by n, that cancels. Then you are remained with only the first term and the last term. So Sn simplifies as 1 minus 1 by n plus 1. To make this simplification, we have written an in this form. That helps to cancel the term easily. Now, therefore, limit of Sn as n tends to infinity is limit n tends to infinity. Substitute this Sn. So 1 minus 1 by n plus 1, apply the limit 1 by infinity is 0, this is equal to 1. Therefore, the limiting value of Sn as n tends to infinity is unique and finite. That means the sequence of partial sums converges to 1. Hence, the series also converges and the series also should converge to 1. Now see second example. 1 square plus 2 square plus 3 square so on up to n square plus so on. It's an infinite series. First, nth term of the series an equal to n square. Therefore, get the nth partial sum of this infinite series, which is Sn equal to 1 square plus 2 square plus so on up to n square. This is the sum of squares of first n natural numbers, which is given by the formula n into n plus 1 into 2n plus 1 divided by 6. So the series is convergent if the sequence of partial sums converges. That means limit of Sn as n tends to infinity value you have to find out first. Therefore, limit of Sn as n tends to infinity equal to limit n tends to infinity. Sn is simplified in this way. So substitute that here. As n tends to infinity, when you apply the limit, gives you infinity by 6, which is nothing but plus infinity. That means limit of Sn as n tends to infinity goes to infinite value. Hence, the sequence of partial sums is divergent. The given series is also divergent. One more example. This is the given series. So when you expand the series, we will get minus 1, plus 1, minus 1, plus 1 and so on. That is alternative plus and minus here. So nth term of this series is an equal to minus 1 to the power n. The sequence of partial sums Sn equal to minus 1 plus 1 minus 1 plus 1 so on up to n terms. So it depends on the value of n. Sn depends on the value of n. So Sn is equal to minus 1 if n is odd. See, first term is minus 1 if you consider. If you consider S2 minus 1 plus 1, it is 0. That means it is 0 if n is even. Sn has two values now, minus 1 and 0. Therefore, limit of Sn as n tends to infinity, even if you apply the limit, it gives you minus 1 and 0, which is finite but not unique. It is having two different values. So, sequence of partial sums oscillates finitely between 0 and minus 1. Hence, the series also behaves same as sequence of partial sums. Hence, given series also oscillates between 0 and minus 1. Now, one more example. Summation minus 1 to the power n into n, which is equal to, when you expand this, you will get minus 1 plus 2 minus 3 plus 4 and so on. So, whenever a series is given, first you write the nth term of the series minus 1 power n into n. Then you have to find out the nth partial sum, which is Sn, minus 1 plus 2 minus 3 plus 4 and so on up to n terms. Therefore, as it is having negative and positive terms, so you will have now two values. So when you consider limit of Sn as n tends to infinity, when you consider n as odd, then you will have only minus 1, minus 3, minus 5 and so on. So it goes to, as you apply the limit n tends to infinity, that value goes to minus infinity, because minus 1, minus 3, minus 5, minus 7 and so on. So going to smaller numbers. Similarly, when you take n as even, then it is 2, 4, 6, 8 and so on. So it goes to plus infinity. The sequence of partial sums oscillates infinitely. Hence, the series also behaves same as sequence of partial sums. The series also oscillates infinitely. There are certain points to remember. See here, the first point is that if an is greater than 0 for all n, if each term of the given series is positive, then we call that series as series of positive terms. This is not the series of positive terms because it has alternative positive as well as negative terms. If it has only the positive terms, then it is a series of positive terms. The next point is that series of positive terms either converges or diverges to plus infinity. There is no other possibility. If it doesn't converge, then it diverges to plus infinity. No possibility of oscillating Third point is that if this given series is convergent, then limit of an as n tends to infinity equal to 0. This condition should satisfy if the given series is convergent. The fourth point is that limit of an as n tends to infinity not equal to 0 means the series is not convergent. We can't say it as divergent. It is not convergent. It doesn't converge. It may diverge or may oscillate. That depends on the given series. If the limit of an as n tends to infinity is not equal to 0, then it is not convergent. If the series is series of positive terms and limit of an as n tends to infinity not equal to 0, then the series must diverge. Here the case of oscillatory series won't appear because we know that series of positive terms either converges or diverges to plus infinity. One more point is that if limit of an as n tends to infinity equal to 0, then we can't conclude that the given series is convergent. That means the converse of this need not be true. The given series may or may not be convergent. Let us see examples for all these points now. See here, let us give an example for this third point. Summation of an is convergent when limit of an as n tends to infinity equal to 0. See, consider this series. We have already proved this series is convergent. The first example which I have given you in the beginning of this video, that shows the series is convergent. Now take nth term of this series. Let us find out limit of an as n tends to infinity. 1 by infinity it is, which is equal to 0. Therefore, if the series is convergent, then limit of an as n tends to infinity must be equal to 0. Now take one more example. This is the second example. 1 plus 1 by 2 plus 1 by 3 so on up to 1 by n and so on. This is the given series. Nth term of this given series is 1 by n. Limit of an as n tends to infinity equal to limit n tends to infinity 1 by n. That is 1 by infinity equal to 0. But this series is divergent series. That is, using P series test, we can say that this series is divergent series. Therefore, if the limiting value of an as n tends to infinity equal to 0, we can't conclude that the series is convergent. It may converge or may not converge. So this is an example. One more example, 1 square plus 2 square so on up to n square. This is the given series. An is n square. Limit of an as n tends to infinity equal to limit of n tends to infinity of n square, which is equal to infinity. So limit of an is now not equal to 0. So whenever limit of an as n tends to infinity is not equal to 0, then the given series is not convergent. Therefore, the summation of n square is not convergent. Therefore, it may diverge or it may oscillate. But now it is series of only positive terms. Hence, the given series diverges. In this case, it is divergent. See one more example. Minus 1 power n into n. Here an is minus 1 power n into n. Limit of an as n tends to infinity has two different values. Minus infinity when n is odd and plus infinity if n is even. That is because a 2n gives you 2n and a 2n plus 1 gives you minus 2n plus 1. So when you apply the limit, it goes to minus infinity and plus infinity. Therefore, limit of an as n tends to infinity is not equal to 0. So if it is not equal to 0, the given series is not convergent. Since limit of an as n tends to infinity is not equal to 0, this series is not convergent. So this is how we check the behavior of series using the sequence of partial sums. I will explain the different tests for convergence of the series in the next video. Thank you for watching.